everyone. So my research subject was about the three famous ontology processes: alignment, mapping, and merging. An attempt will be made to find how to make machines use language from abstraction and concepts, solve kinds of problems now reserved for humans, and improve themselves. For the present purpose, the artificial intelligence problem is taken to be that of making a machine behave in ways that would be called intelligent if a human were so behaving. This was a result of the 1956 conference organized by John McCarthy at the Dartmouth University, entitled the Dartmouth Summer Research Project on Artificial Intelligence. It was a summer workshop that lasted approximately 8 weeks and widely considered to be the founding event of artificial intelligence as a field. Since then, AI has grown into an independent field of research, drawing ideas as well as techniques from various fields. Within this large field of research, there are many areas such as machine learning, perceiving and acting, operation research, problem solving, knowledge representation, and automated reasoning. Here, we think about the area of knowledge representation. So knowledge representation and reasoning is an area in AI that concerns with how human knowledge can be represented in a structured way so that a computer is able to manipulate the knowledge and other relevant information in an automated and efficient way to perform reasoning tasks and to draw conclusions from known facts and knowledge. Different methods and formalism for representing human knowledge in computer in a structured and organized way have been developed, including first-order logic, semantic networks, object-oriented models, description logics, and ontologies. Among these formalisms, ontologies have attracted more and more attention in the last decade. Ontologies are now widely used as a means of conceptual modeling or domain modeling in various areas of application. They are semantic data models that define the types of things that exist in our domain and the properties that can be used to describe them. They are generalized data models, meaning that they only model general types of things that share certain properties, but don't include information about specific individuals in our domain. There are three main components to an ontology, which are usually described as follows: classes, the distinct types of things that exist in our data; relationships, properties that connect two classes; attributes, properties that describe an individual class. So here, for example, we have company, employee are classes, work for has contract with are relationships, and for attributes we have the consults or the title of the project, which is sale process. Let me show you an illustration which fits our subject today. A group of blind men heard that a strange animal called an elephant had been brought to the town, but none of them were aware of its shape and form. Out of curiosity, they said, "We must inspect and know it by touch, of which we are capable." So they sought it out, and when they found it, they grouped about it. The first person whose hand landed to the trunk said, "This being is like a thick snake." For another one, whose hand reached its ear, "It seems like a kind of fun." As for another person whose felt it task, "Stunning the elephant is that which is hard, smooth, and like a spear." The blind man who placed his hand was upon its leg said, "The elephant is a pillar like a tree trunk." Another one placed his hand upon its side, said, "The elephant is a wall." The last felt its tail, described it as a rope. So each one of them was partly in the right, and all were in the wrong. The same thing applies when talking about ontologies, considering the fact that they are context-dependent projection, or in another term, a model of the reality. So when modeling, we only focus on aspects that are necessary for the app we have in mind. Thus, we should keep in mind that ontologies are not the reality. They are only a description of the reality, and they are always in the eye of the beholder. So the model is never the reality because we leave out aspects of reality, and different ontologies might represent the same knowledge. Ontology mediation is a process that reconciles differences between separate ontologies to achieve semantic interoperability by performing alignment, mapping, and merging. Assuming that we have a provider which uses a terminology 1 and a requester which uses a terminology 2. In order to establish communication between them, we are going to need mediation for those two terminologies and thus allow the process of communication successfully. We distinguish two principal kinds of ontology mediation: ontology mapping and ontology merging. With ontology mapping, the correspondences between two ontologies are stored separately from the ontologies and thus are not part of the ontologies themselves. The semi-automated discovery of such correspondences is called ontology alignment. When performing ontology merging, a new ontology is created, which is the union of the source ontologies. The merged ontology captures all the knowledge from the original ontologies. The challenge in ontology merging is to ensure that all correspondences and differences between the ontologies are reflected in the merged ontology. In some sources, we find that the mapping and alignment, if we can say, are merged into one single process, which is matching. So then we talk about matching and merging. Later, we are gonna see them in detail with two examples per each process. So, to summarize, ontology mapping is mostly concerned with the representation of correspondences between ontologies. Ontology alignment is concerned with the discovery of these correspondences, and ontology merging is concerned with creating the union of ontologies based on the correspondences between them. Ontologies can differ in multiple forms, as depicted in the figure. We see here that all of these three are saying the same thing, but in different representations or ways. Now, the question is how to align them. To do so, we have to figure out which kind of heterogeneity class this kind of ontological difference might belong to. So here we have types of ontology mismatches. Basically, we have two types: conceptualization mismatches, which are mismatches of different conceptualization of the same domain, and explication mismatches, which are mismatches in the way a conceptualization is specified. And each of them fall into other subkinds of mismatches that are shown here. So let's see these three processes in detail. And the beginning will be with the alignment process. Ontology alignment is the process of discovering similarities between two source ontologies. The result of a matching operation is a specification of similarities between two ontologies. The ontology alignment consists in generating a set of correspondences between entities. These entities can be concepts, properties, or instances. And it follows this simple process we can formalize in the following ways. So we start with two source ontologies, and we have some kind of input alignments, and this is the input of the matching process, which also take into account some models, like for example some parameters as weights, or some external resources as knowledge bases or rules. They guide or help the matching process, and the output here is the alignment called A prime, and it's a set of correspondences of mapping between single ontological concepts in these two ontologies, O1 and O2. In the following, we will give an overview of one approach of alignment, which is answer prompt. So, answer prompt is an algorithm which uses relations amongst terms in an ontology and the set of answers to determine which other terms in the ontology are semantically similar automatically. Answer mean pairs of similar terms defined by the user or automatically identified by lexical matching. So this algorithm treats an ontology as a graph with classes as nodes and slots as links. Then it analyzes the path in the subgraph limited by the answers and determines which classes frequently appear in similar position on similar paths. These classes are likely to represent semantically similar concepts. The input of the algorithm is a set of pairs of related terms from the source ontologies. And the central observation behind answer prompt is that if two pairs of terms from the source ontology are similar and there are paths connecting the terms, then the elements in those paths are often similar as well. Therefore, from a small set of previously identified related terms, answer prompt is able to suggest a large number of terms that are likely to be semantically similar as well. And the output of the algorithm is, for each set of parameters, a set of related terms as determined by answer prompt is given. For example, suppose we identify two pairs of answers, class E and class B, and class H and class G. There is class E from one ontology is similar to a class B in the other ontology, and class H from the first ontology is similar to a class G in the second ontology. The following figure shows one path from E to H in the first ontology and one path from B to G in the second one. We traverse the two paths in parallel, incrementing the similarity score between each two classes that we reach in the same step. For example, after traversing the paths, we increment the similarity score, which is a coefficient that indicates how closely two terms are related between the classes C and D and between the classes E and F. We repeat the process for all the existing paths that originate and terminate in the answer points, cumulatively aggregating the similarity score. So, in this example, we will consider the following two pairs of answers for the two ontologies O1 and O2, trial and person. Using these two pairs as inputs, the algorithm must determine pairs of other related terms in the two ontologies. It generates a set of all paths between trial and person in both ontologies, and it considers only the paths that are shorter or equal to a predefined parameter length. So here we will consider a pair of paths in this set that have the same length. We will choose then trial protocol study site person in the first ontology and trial design building person in the second one. As it traverses the two paths, answer prompt increases the similarity score for the pairs of terms in the same position in the path. For the two paths in our example, it will increase the similarity score between protocol and design and between study site and building. I'm gonna skip the next algorithm and we will move on to the mapping process. Mapping is a formal expression that states the semantic relation between two entities belonging to different ontologies. Given two ontologies, O1 and O2, mapping one ontology into another means that for each entity in ontology O1, we try to find a corresponding entity which has the same intended meaning in ontology O2. Let's keep in mind that complex mapping are not addressed here like end-to-end mapping or concept-to-relation mapping. We only focus on one-to-one mapping between entities of the same type. The algorithm that we are gonna see in the mapping process is MAFRA. So MAFRA is an abbreviation of Mapping Framework for Distributed Ontologies. It's an interactive, incremental, and dynamic framework for mapping distributed ontologies. It takes as input two ontologies, the source and the target, normalized and already represented in RDF schema with their instances in RDF. The main concept here is the semantic bridging. Its role is to semantically relate entities from the source and target ontologies by encapsulating all necessary information to transform instances of one source ontology entity to instances of one target ontology entity, and the output is an instance of the semantic bridging ontology. As for the architecture, the framework consists of 5 horizontal modules describing the phases that are considered fundamental and distinct in mapping process. The first is left and normalization. It's used for lifting the content of the ontologies to additive schemas and normalizing their vocabularies by eliminating syntactical and lexical differences. The similarity phase allows the computation of the similarities between ontology entities as a support of mapping discovery. The semantic bridging, which is the main phase in the whole process, is here to establish correspondences between similar entities in the form of so-called semantic bridging. So here we define the mapping. The execution phase is the exploitation of the bridges or the mappings for instance information. And finally, the post-processing is revisiting the mapping specification for improvements. And also it consists of 4 vertical components run along the entire mapping process, interacting with horizontal models. Evaluation focuses on maintaining semantic bridges obtained by the semantic bridge model. Domain constraint and background knowledge to improve the quality of similarity computation and semantic bridging by introducing background knowledge and domain constraints. Cooperative consensus building is responsible for establishing a consensus on semantic bridges between 2 communities participating in the mapping process. And finally, the graphical user interface. So MAFRA is currently under development within the CON, Ontology, and Semantic Web Framework. For the moment, they achieved the implementation of 4 models of MAFRA: the similarity discovery model, the semantic bridging representation, the graphical user interface, and the execution engine. A screenshot of the user interface for mapping specification is presented in the following figure. In this example, 2 ontologies have been opened side by side, and in between, an instance of the semantic bridging ontology is created using a simplified user interface. I'm gonna skip the second example here, and the last process is merging. So ontology merging is the creation of a new ontology from 2 possibly overlapping source ontology. There are 2 approaches in the process of merging. In the first approach, the input of the merging process is a collection of ontologies, and the outcome is a new merged ontology which captures the original ontologies. A prominent example of the approach is prompt. In the second approach, the original ontologies are not replaced, but rather a view called bridge ontology is created, which imports the original ontologies and specifies the correspondences using bridge axioms. OntoMerge is a prominent example of this approach. So let's see the algorithms of the merging process, and the beginning will be with the prompt algorithm. So prompt is an algorithm and interactive tool of merging 2 ontologies. The central element of prompt is the algorithm which defines the number of steps for the interactive merging process. The steps of the prompt algorithm are the next. The first activity is to make a list of suggested operations. Here we identify merge candidates based on class name similarities. The result is presented to the user as a list of potential merge operations. Then the second activity and the third is to select and to perform next operation. Here the user, basically the ontologist, chooses one of the suggested operations from the list or specifies a merge operation directly. Then the system performs the requested action and automatically executes additional changes derived from the action. The fourth activity consists of finding conflicts. The system determines conflicts introduced by the last action and finds possible solutions to these conflicts and display these to the user. And finally is to update the list of operations. Here the system creates a new list of suggested actions for the user based on the new structure of the ontology. Let's suppose that we want to merge the ontologies of the following figure using prompt. So the first ontology, we have the top class travel, we have two subclasses, train, travel, and flight, and under flight we have American Airlines flight and British Airways flight. And in the second ontology, we have always at the top the class travel, then we have train, travel, and ship, and under train travel we have travel in high-speed train. So the initial list of possible operations for the two ontologies of the previous figure will be the one that appears in the following table. We propose to merge those classes that have similar names in both ontologies, like travel and train travel. And we also propose to make a deep or shallow copy of the classes that are not common to both ontologies, depending on whether they have subclasses like flight or they don't. The second activity is to select next operation. The ontologist chooses an operation of the list, and this decision might be based on different aspects, what he wants to focus on, what he considers important, etc. For example, the ontologist might decide that he is only interested in merging parts of the ontology and just ignore other parts. But let's suppose that in our travel domain, the ontologist chooses to merge the class travel of both ontologies. The third activity is to perform the selected operation. The prompt plugin executes the operation selected by the ontologist in the previous activity. After this point, the ontologist might order the prompt plugin to carry out additional changes associated to the proposed operation. For instance, when the merging of the class travel of both ontologies is carried out, all the original slots of travel in Ontology 1 and Ontology 2 can be included in the resulting class. The fourth activity is to find conflicts. This activity is performed by analyzing the resulting ontologies, and many conflicts might appear in the resulting ontology after the execution, like naming conflicts or slot value restrictions or dangling references. The fifth activity is to update the list of operations. For updating the lists, the prompt plugin does not only consider the linguistic similarity, but also the structure of the ontology. This activity could be carried out with the algorithm answer prompt. So the following process is repeated until the two ontologies are merged. After performing several iterations, the resulting ontology of our example might be the one appearing in the following figure. So here we have the top class travel, under it we have train travel, ship, and flights. Under flights we have American Airlines flights, British Airways flights, and under train travel we have travel in high-speed train. So the next example of the second approach is OntoMerge. OntoMerge is an online approach in which source ontologies are maintained after the merge operations. Whereas in prompt, the merged ontology replaces the source ontologies. The output of the merge operation in OntoMerge is not a complete merged ontology as in prompt, but a bridge ontology which imports the source ontologies and which has a number of bridging axioms, which are translation rules used to connect the overlapping parts of the source ontologies. So here we have some kinds of concepts in the ontology. So ontology is defined as a formal specification of vocabulary of concepts, including axioms relating these concepts. A sub-ontology S of ontology N is an extension of the vocabulary of N, introducing new concepts, new axioms, and new facts. The ontology translation problem is to translate the concepts and relationships of the one ontology, which is the source, into the vocabulary of another ontology, which is the target. Hence, the first step in translation is to find ancestors of the source and target for which a merged ontology exists. There is a common framework that relates them. Using this common framework, ontomerge educatively translates from one vocabulary to another. In terms of tools, we can find two types. Language-dependent tools. These tools are characterized by their tight relationship with an ontology language. For example, we have Ontology server with Ontology language, OIL-ED with the OIL language, and language-independent tools. These tools are characterized by their open architecture, which allows an easy extensibility and integration with other applications, and by their language-independent underlying knowledge model. The following table summarizes a comparison about the most famous tools. Here we will single out Protege and Amin because we are gonna see some examples with them. So they both released in 2004. They are free and they can import or export to many formats and quite the same one. Now let's move on to Prodigy and see our first example with it. Since its global third version, Prodigy does not support prompt plugin. So here we are gonna see how to merge two ontologies using Prodigy 5.5.0. After the mapping process and identifying all mappings between the two source ontologies, we will follow these steps in order to merge our ontologies. First, we will open the two source ontologies in the same window. So here we have the first one, and in the same window we will open the second one too. We can visualize them here. So I will use the vowel plugin. Then we will go to the refactor tab, merge ontologies, and we will select them both in order to merge them. Press continue. Here we will select the merge type, and I always prefer to merge them into a new one so I can keep the source ontologies. Here we specify the ontology area, which is the identifier of our ontology. We can name it merged onto. Press continue and specify the location. We can choose multiple formats. I'll stick to RDF's XML syntax and press finish. Here we have the ontology result, which is merged onto. We can visualize it in the Intograph plugin. I'm gonna open them all. So here we can see the two different classes, family car and family car, representing the same thing, are presented in the resulting ontology. there is a need to change the name of one of the classes and rename it to the name of the other one to avoid the conflicts. So this is the problem of the merge algorithm proposed by prompts. If we click on a class and change array, if I choose to show the full array, I'll say that they only copy the array of the classes from the source ontologies. So here basically we want to have merged onto hashtag family car. So we are gonna do this manually, and the results will be the following. So let me reopen it. So this is a work I have done before. Here we have only one class of family car. Within it we have the two subclasses BMW and Porsche. And this is the result of the merging process in Protege. As for the example of AMIM platform, the following work is based on all API implemented in Java and ready to be integrated in AMIM platform. The merger class contains two methods: merge ontologies, which is the main method. It contains the steps of the merging process, and the second one is rename arrays. Now this method fixes all the problems that we find in merger of Protege. So all the manual work is no longer needed. We can visualize the results in Protege. Now I'll open the resulting ontology, which is this one, and we will visualize it using Ontograph plugin of Protege. So here we can see that it's pretty much the same result that we find using several iterations in Protege merger.